They're both from the website. One, the YouTube one is in the upper right. The other one is when you click on regular, it's the first link. It says solved problems, I think. Okay, questions on any of these problems? Oh yeah, also due to popular demand, this is due tomorrow. So then you do have to go through it and do it. Yeah, so make sure like you at least test it and then jot down a few words on this due tomorrow. Okay, so questions on this, on what you got wrong.
Wait, I don't get number one.
Okay, so number one, the wavelength goes from the same to the same. There you go.
When they
Nope, because this whole thing's, well, okay, let me do it like this. From the same to the same, which means middle, back to middle right there. And that is, which means 2 meters. Okay, other questions? Come on. Oh, how do I do this? Alright, open this at preview. Okay. Good. Now I can tweak that way. And then I can do this. Excellent. Arr.
Is that mine?
It's funny, some kid, I found a phone outside on the ground saying, oh yeah, I had a kid come in and said he lost it. And the teacher says, is there a horse? So the kid goes, yeah.
Wait.
I mean, does that not seem stupid?
Yeah.
They should have said, describe it. Tell me something unique about your phone. But is there a horse on the back? Kid's like, yes. So, I don't know. I give it to, so the teacher gave it to him. So oh well. All right. Anyways. Okay.
You should have went out afterwards.
Should have said, what type of horse is it? All right. So here, unknown resistor, and this resistor. So let me go. Try to zoom in a little bit, just for funsies. Make it super big. Oh, look at that. Big is fun. Okay, so this 100 ohm resistor, blah, 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 is connected to a 10 volt battery. So this is the total EMF. We know that. And then we know that the 100 ohm resistor has a potential drop of this. These two things are connected in series, which means what is true about both resistors? They have the same what? Current. They have the same current. So that means if I look at the second one, if I look at the resistor, the 100 ohm resistor, right? I can use that to find the current through the 100 ohm resistor, which will be equal to the other to the total current, right? Because it's in series. So I use V equals IR, or I use I equals V over R. Be 4 volts divided by 100 ohms. So that gives me a current of 0.4 amps. Okay, that is the total current. So I can find, using V equals IR, using total, total, and total, I can find the total resistance and say V total over I total is going to equal that. Do you see that this is different from this? But by the fact that this resistor is, this is just for the 100 ohm. Do you get what I'm saying there? So we use the 100 ohm voltage and resistance to get the current. That's the same as the total current. So then since we know the total current and the total voltage, we can find the total resistance. So the total voltage is 10 volts divided by the total current, which is 0.04 amps. That's going to give me 1,000 divided by 4, so that's 250 ohms. And then R total is equal to R100 plus R. Therefore, R is equal to R total minus R100. giving me 150 ohms. Ching. So, for this problem, the trick is you have to use one resistor to get something, some information, so that you can go back and look at the total circuit to get the final result. So it's like you have to use the same equation twice, and then you have to use your understanding of series circuits. Yeah.
So just to clarify, when you're finding the amplitude, it doesn't matter. Finding the current, it doesn't matter that you don't have all the resistance because the current is the same for both.
Because it's a series circuit. Yep. Okay, questions? All right. We shall move on. Any other questions on this page, on the first page? 9? So there are no more questions? Okay, bad joke, I guess. Thank you for getting it. I appreciate it.
Oh.
Do you have any questions? 9.
Should crop that out.
Yeah, I know this. That's all right. It's not racist because it's about white people. Okay. As a oh yeah, this is just, do you understand what a transistor can do? So I have to ask questions about transistors. That's the state standard. So then it's just understand the basic concepts of a transistor. It's a remote switch. It also does it's an amplifier. What does it amplify? It amplifies current. So which one of these amplifies current?
The wording of it.
So these two decrease, and it doesn't amplify voltage.
The wording of it just made it sound really daunting.
Yep. Yes. Sorry, what? Yes. You know how, like, do you remember, like, I said it's like two circuits, and one circuit affects the other one? The collector current is the output on the bottom. I'm not that worried that you know all of it. Just know that transistors can amplify. They're remote switches, or they can amplify current. The emitter and the collector are different parts of the transistor. Like the part where the electricity comes in is the emitter, the part that comes in is the collector, or comes out as a collector. So it's just a definition, that's all. There won't be anything more than that on the file. Number 10. Okay, which of the following electromagnetic waves has the lowest frequency? This, you just got to remember. Because remember, we did red, orange, yellow, green, blue, indigo, violet. Then you had UV, then you have X-ray, then you have gamma ray. Down here, you have infrared, then you have micro, then you have radar. There's actually one, I think it's in here somewhere, that they use at the airport. You know that big machine where you have to stand like this and they scan you? They use millimeter waves. Anyways, so this is, lambda is big, this lambda is small. This frequency is small, this frequency is big. So, based on this, which one? Red. Because red has the smallest, or has the longest wavelength, and therefore the smallest frequency. Okay, other questions on the next page? So page 2, any of those? 12. Okay. Okay, Diagram shows coil of wire. Which way is the current going? Left to right? Clockwise or counterclockwise? Counterclockwise. Do you see it? Okay. Now, so the north pole of the coil is going to be the side where the B field is coming out of it. Where is the B field coming out? Well, if I follow my fingers up this wire and I'm behind this cylinder, when I wrap my fingers around, do you see my knuckles are pointing this way inside the coil? So the B field looks like this.
Okay, why do you wrap your fingers around?
Because it's a wire, so I'm trying to find the B field, right? And whenever you have a wire and you're looking for the B field, you wrap your fingers. When you're messing with force, then you use this.
Oh, so wire is the current, right?
Yep.
The force is just, oh,
Trying to hold something up, trying to push a wire, trying to push a charge, you have your hand over.
alright, cool.
Okay, questions on that one?
So it's
Going out of the positive and not out of the negative.
Because it's always out of the positive.
Okay, I got what you're saying.
That's right. Now, you maybe electrons actually leave from the negative. So the real current that's actually happening in a circuit is from the negative. But we need something called conventional current. We use something, we don't need it, but we use conventional current. So. Okay, other questions? Yeah. Hold up. Ooh, it's too big. Okay. Diagram shows a current. What the heck?
If you're in a recording.
That's weird. The diagram below shows a current carrying wire. Electromagnetic. Electron flow is directed towards the. So if, okay, where if this wire, the force on the wire is directed out of the page. So this wire is being pushed towards your face, okay? Towards your face. So your first response is to put your fingers here and to put your palm. First answer might be to the right. But what does it say? Electron flow. So that's opposite. So you could use your left hand and that will show you it's to the left. Or just whatever your right hand tells you, do the opposite. Okay, questions on that one? No? Okay. Moving on. Other questions? Yeah. Yes. Take the pass. No other questions on this page? Yeah. 14. 10 ohm and 20 ohm resistor connected parallel to a constant voltage source. If the current is 4 amps, then the current through the 20 ohm. Okay, so what you do is you first, let's say there is V equals IR for the 10 ohm, and there is going to be V equals IR for the 20 ohm. Does that make sense to you? Right? For each resistor in a circuit, I can use Ohm's law. Right? Okay, so now what I'm going to do is I know that the 10 ohm current is 4 amps. So I'm going to find the voltage. So the voltage in the 10 ohm is 4 amps times 10 ohms. That's 40 volts. Now, these two resistors are connected how? In parallel voltage. It's the same. Okay? It equals whatever, however you want to do that. So it's the same. So that tells me that this voltage is that voltage. So now I can say I of 20 is equal to V of 20 over R of 20. So then I get 40 volts over 20 ohms. That gives me 2 amps. Yeah. Perfect. Exactly. Did you hear what Hillary said? It's important for you to remember that. Resistors in series have the same current. Resistors in parallel have the same voltage. Just got to remember that. All right, any other questions on this page? 15. A motor is used to produce. Thanks, man. Diane. You're getting awards, so make sure you show up the awards there. That's like Diane. Is it? I don't know where it is. I don't know where it is. All right. So a motor is used to produce 4 waves each second in a string. What is the frequency? F is the like kind of like the events per second. So it's 4. Just you have to know that's what frequency means. Like if I tap the board, 1001, 1002, 1003, 1004, 1005. What's that frequency?
Board.
Yeah, I'm tapping it 1001, 1002. I'm tapping it 1 time every second, right? So that's 1 hertz. Yeah.
Could you explain
16? Oh, okay, doke. As a wave travels through a medium, particles in the medium, what type of wave is traveling through the medium? Oh yeah. Remember, we talked about, so actually all 3 of this isn't, this kind of wave, have you ever slapped a stop sign?
Yeah.
Or a street sign? It's not that hard, but like on the side, what does it do? It goes like that. Ding, that's a torsional wave. So when it oscillates back and forth, that's a torsional wave. Okay, yeah, yeah.
That's like the bridge video showed us, right?
Yeah, sure, that was what it is. Now, a longitudinal wave happens when you are in a medium. This transverse wave happens when you are between media. So a torsional wave is when you twist. Longitudinal wave is when you're in one consistent medium. Transverse wave is when you're between mediums. Yes? Sure, you could. For example, like if I'm like, I don't know, whatever, like the Hulk, and I'm underwater, and I go like this.
Hulk smash.
What's going to happen? Yeah, there's going to be this wave of energy that travels out. Does that make sense? Now, underwater, will it look like a wave like this? No, it's going to look like water. I'm not going to see anything. I'm just going to feel the wolf go by me. But what happens when that wave hits the surface? Yeah, that energy is going to energize the water on the surface, and it's going to push it up. Well, there's no water above it to push back. So when it gets pushed up, it sucks in the water from around it. That's how the bubble forms. So this big wave goes up until it runs out of energy, then it slops down. So that would be a transverse wave. So whenever you see a transverse wave, something that looks like this, that is at the boundary between 2 different types of media. Okay. Other questions on this page? All right, so we're going to move to the next page. So we're on 20 to 25. Any questions on this? 20 to 25. Any questions? Going once?
21.
Yeah. Which one?
21.
21? This is kind of like a question that we had already. For this one, you basically use 2 different things. First, you use Lenz's law to determine which direction the current is flowing. So, first, figure out the direction of the current. How it flux if that wire is moving to the left? It's decreasing. So what does Lenz's law say? The change. So then we take what Kashi said, which was now we have to go with the B field. Does this make sense to you? Right? Because the B field's diminishing, so you have to go with. So do it. Go with it. Point with your hand, everyone now. Go with the B field. You should be pointing at the board. Okay? So Now put your hand on the wire. It's your palm. Your palm always touches the wire. And that means the current is going to flow down like this. And it's moving clockwise. Is there anybody who doesn't get that? So you should be able to first determine that the current will flow will flow clockwise. Yes? Questions? Do you see that the flux is decreasing? Okay, you know what flux means. Just the number of little dots or little X's, right? So that number is going down. So then, Lenz's law says, fight the change. So if the change is that you're getting less and less magnetic field, what do you have to do? You have to give it more. And that's why you take your fingers and you point it into the board. Because each one of these is one of those little X's. And by sticking your fingers in there, you get more, you're filling up the X's. Now, you have to put your hand on the wire. So you see on the left side it's like that, on the top it's like this, on the right it's like that. See what I'm saying? Into the field. I'm going with the field. And that just naturally shows me, because my palm has to be on the wire. That is on the top. But, no, sorry, what? Which one? Well, oh, you mean this? Where could you be like this in there? See, you can't be like this is inside. Watch, try it. Remember, your thumb has to go with my fingers, and your palm has to touch it. See, this is that limit. So go ahead, put your hand in. Now put your thumb in there, good. See? No, you can't. You physically can't do that. Because you would be on the outside. But you have to be on the inside. See, so you can't go like this and go underneath. Because you'd be outside the loop. You have to be inside. Okay, any other questions on this? Yeah, I know.
Pretty sure I got it. So because it's decreasing, you go. And since the positioning of your hands, it goes from.
Well, we don't have our hand positioned at all, right?
Oh, okay.
We just say the B field is decreasing,
Right.
which means I have to add to it. Because I have to fight whatever the change is. So add your fingers to that B field. Mm-hmm. That's subtracting. That's added.
Okay.
But make sure your hands are straight.
Wouldn't that be going to the left?
On the bottom it does. Now go up to the side. See?
Oh, so that
And the
way.
top.
Oh, okay.
See? And then corner.
Okay.
Okay. That's just part A. Well, it's not even part A. It's just the first part. So, is everybody here okay with the fact that the current is moving down?
Yes.
Anyone? Now, take your right hand again, and we're doing something totally different. All I'm telling you is this current is moving down. Which way is the B field going to push that wire? Put your fingers in the direction of the field. Put your thumb in the direction of the current. Where's your palm pointing? See? So the field is going to push this to the right. And that's the answer. Your fingers have to go in the direction of this B field.
Oh, because it's going away.
Yeah, so it's going away, so you got to point them away from your face.
Oh, no, force.
Questions? This is a good question. This adds up everything that we did in chapter 22 and 23. It's a summation of all that stuff. Yeah.
So we're talking about like Lenz's law, defining the field,
It depends. Lenz's law says you fight the change. So if the B field's getting bigger, you're going to oppose it. If the B field's getting smaller, you're going to add to it.
and that's how I find the direction.
And yes, and then you say, okay, now I know whether I'm going to add or I'm going to subtract. I'm going to increase or am I going to oppose? Once I know that, now I look at the B field. And if it's pointing into the board, now I know which way to point my fingers. Okay, questions? 24. Okay, no. For this one, who asked for this one? Okay. Then what is the current here? How about this? How about this? Let's take a look. These are people. How many people are walking down that part of the hallway? How many people are walking down this part of the hallway? How many people must be in this part of the hallway? 6. Think of current like people, and it works. Right? Because you can't have students disappear. You can't have students magically appear at school. Right? Remember, there's no disapparating in school. So, oh yeah, like current is based on actual physical charges, which means matter doesn't just appear. So if there were 10 amps of current here, and 4 of those amps are here, where's the rest? It must be here, because this broke into 2, right? And that means this is going to be 10 going back. Does that make sense? Okay, that has nothing to do with answering the question. I just wanted to see if you could do it. Now, what I would do is I would just say V equals IR. Because whatever the voltage is across this is the same as the voltage across this, which is the same as the EMF. Because it's a parallel circuit. See, the battery connects directly to this resistor. Therefore, whatever the voltage drop is across this resistor has to match the EMF of the battery. Well, the voltage, the electric potential of the battery. And then 120 just comes from 4 times 30. It works here too, in case you didn't notice. 6 amps times that. Yep. Okay, questions? Yeah. Okay, hang on, let me just put this one away. Which one did you say? 23. Okay, let's go back to 23. What is the frequency of a wave? It's that you just have to know. You have to know this. Frequency is 1 over period. That's like a definition.
1 over period?
Yeah. For example, if I tap 1 time a second, how long is the duration between taps? 1 second, because frequency was 1 hertz. So when you invert the frequency, you get the period, which is 1 second. Because it's 1 tap per second. And if you flip that, you get 1 second per tap. Yeah, they're just inverse. Okay? Other questions on this one? Yeah.
25.
20 what?
25.
Wait, did I just do 25?
Nope.
Oh, okay. Okay. Which way is it going to go? Down. They told you it's +2.
Wait, but my question was, how do you know when it accelerates and when it doesn't accelerate?
Because of this. Remember electric field strength? So F is equal to EQ, which is equal to MA. So the electric field applies a force on that charge. That force means it's accelerating. Because then there's nothing pointing up, right? If this was flipped so that it was negative up here and plus right here, then it would not be obvious. Because you could pick the right electric field that would just make that charge sit there in the air. Okay, other questions? Shall we go to the next page? I suppose. Okay, any questions from here? 26? All right. What is the power of the 30 ohm resistor? Huh? Oops. Since P is IV, which is V squared over R, which is I squared R, pick your poison. What is the power on the 30 ohm resistor? We know R and we know V, so why not use this one, which gives us 900 divided by 12. Oh, whoops, I'm sorry, just kidding. Losing my mind there. R. Oh, I squared R. Ha, just kidding, that one.
Actually, you can still use the B squared on it, so it would be 144 over 30.
Oh yeah. Oh, I screwed the. Okay, I flipped it. All right, very good, very good. I flipped it. Sorry, it should have been 12 squared over 30. Whew, thank you. So 144 over 30. There you go. So I was looking at the other number. I'm like, it doesn't add up. to that. Sorry about that. Okay, had my mouth done what, or had my brain done what my mouth said, it would have been fine. Does that make sense? Questions? Okay, moving on. What else? 27. Electric iron has that many. So basically, you just have to say, they want to know, like, this is a power question. How do you know it's a power? Because they're talking about heat. We're not doing thermodynamics anymore. So if you see the word heat, that means it's about power. Remember, power is heat or energy per time. Power is also IV, right? So then IV is Q over T. So then Q is equal to IVT. So I is 10, V is 120, and T, so then you get 3.6 times 10 to the 4. You have to understand what power is. That power is joules per second, right? You have to understand that. You have to know that. Okay, other questions? 28. Okay, remember, we have like 10 more minutes, so make sure that we're picking useful. Like that last one, you should have known that one. That wasn't anything weird. It's just power. So this, what happens to the air is removed from the jar?
Yeah, 28, I don't have to, yeah, I like misread it.
Oh, okay, very good. I like those kind of questions. We can move on. Great. All right, next, what else? Anything else from this page? Yeah.
33, what's interference?
Interference is when they add up. Diffraction is bending. Diffraction is splitting. Reflection, obviously, is bouncing. So, take 3 waves. If I shine, oh, okay, light hitting a mirror does what? Obviously, it reflects, it bounces off. Light coming from a pencil that is in water, that's halfway in the water, what does that do? Bend, right? Because you see the pencil looks like it's weird, like it's split or it's bent. Light going through a piece of glass and making a rainbow on the wall is doing, it's diffracting, it's splitting. Interference is when it just adds up. So interference is, do you remember the day I played the sound and you had to move your head? Maybe not here? No, okay. Well, you know how like one person whispering is no big deal. If you have everybody in the gym, 1,800 people, and they're all whispering at the same time, right? All of those sounds add up. And so it becomes loud, even though every individual person is just barely talking, right? That's an example. Interference can actually be constructive or destructive. Constructive means louder. Destructive means softer. Anybody ever use sound canceling headphones? Yeah. I don't think Beats are actually sound canceling. It would have to be Bose or something. Yeah.
32.
Okay, so 32, orange light has a frequency. What's a wavelength? Just use V equals F lambda. Solve that. You should know this. And then you know that the speed of light is what? 3 times 10 to the 8 meters per second. So you use this frequency, solve this equation, you get equal to C over F. So that's 3 times 10 to the 8 divided by 5 times 10 to the 14. And you get your answer of 6 times 10 to the minus 7. Usually what we do is we say 600 nanometers. And you should know the full range. Did I do this already? I did that already in here? Okay, cool. I mean, today I did that. Okay, good. All right, moving on. Next.
38.
38. If the frequency of sound, blah, 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 blah. Okay. If you, like, let's take a look at this wave right here. If we look at this wave, okay, if I change anything having to do with this direction, I change the wave, or I change the speed, right? Because you cannot change, if you change, you don't want to change frequency. When waves travel from one medium to another, they don't change frequency. They change length or speed, but they don't change frequency. So the only way you can change a wave and not change its frequency is this. That's amplitude. And amplitude is volume. So you can make a sound louder, and it stays the same sound, right? Whether I talk like this, whether I talk like this, it's the same, like the same frequency of my voice. It's just a matter of amplitude. Okay, so that's why this is this. Questions? All right, moving on. Other questions on this page? Anyone? Anyone? Bueller? All right, thank you for the courtesy laugh. All right, here. Which one of these correctly represents the field? This is a fun one. So start with D. Which way is the current going? Clockwise, like that. First of all, do you see it? From plus to minus. Does everyone see the currents going clockwise? Okay, now take your thumb, put it on the wire, and go up. Do you see I'm behind this coil, this rod or whatever? And when I'm behind the rod, which way are my knuckles facing? To the right. Which way are these arrows pointing? Wah, wah, wah. If we were going to draw this the way it should have been like this. Based on this battery. Or I could have flipped the battery.
Why did you put it up like this?
Sorry? Doesn't matter. Watch. See this wire? Which way are your fingers pointing here? Which way are your fingers pointing this way? Over here, over here. See, you can't, because this way you're looking at the fingers on this side, right? Well, if you flip it over here, now your fingers on the other side. It's different. You have to use your fingers that are on the same side. Get it?
That's perspective, basically.
Yeah, exactly. You have to make sure that your finger's in the right orientation. So, now, let's go to this one. Obviously, which way is the current going? Same. Clockwise again. Now, put your fingers here. Follow up. Which way are my fingers pointing? Yeah, to the left. Do you see the difference between these two? See? This one goes behind, this one goes in. Then, we move on to this one. Which way is the current going? Yes, counterclockwise. Counterclockwise. Do you see that? So now I take my fingers and I have to go behind this thing, which means they're pointing out like that. Wrong. Sure. The best way to explain it is to make you do it. This is that bar thing, right? And then that wire goes behind, is it not? This is oh, really? Okay, anyways. So the wire's over here. So wrap your finger around the wire. This is that bar thing through the center. And then this is the wire. So wrap your finger around the wire. Look which way your knuckles are pointing. Touching the bar. Yeah, see they're pointing that way. See it? Go this way? Yes, exactly. See it? Exactly.
Wait, so I still don't get the difference from when it's behind to when it's in front.
Watch. Okay, so here's the bar. And we're going to do this one where the wire goes behind, right? So this is the wire, so put your thumb on it, it's behind. Look which way your fingers are pointing. No. The finger's touching the bar. See? Now it's on the front. Which way your finger's pointing.
My fingers are pointing that way.
But it's only the fingers touching this thing. Not these. It's gotta be this, the ones touching this.
Oh.
You get it?
Yeah. Alright.
Because the ones touching that are inside the coil. Remember, we're only concerned with your fingers inside the coil, not outside the coil. Okay, it's gotta be inside. Okay? And so then,
Got it.
we go to the last one, and we hope that the answer is A, because so far, none of them have been correct. So let's try it. What's the current?
Right.
Counterclockwise. Let's call this counterclockwise, okay? Because right and left doesn't matter height. Now, let's take a look. Here's my thumb. Ding, ding, ding. We have a winner. And that's why that one's bolded. And that, ladies and gentlemen, is the entire tamale.